Okay, so let's continue. Last time we took a review on the Hong's rules and how this, electronic configurations look like in the realistic materials, and we know that these electrons or spins should follow this Hong's rules. And for this partially filled levels or shells, we have a net magnetic moment, and that is the source of all this magnetic orders. And today we will take another brief review of all different kinds of magnetic orderings in solid states, including paramagnetic states and ferromagnetic states and antiferromagnetic states, and also ubiquitous universal diamagnetic material. So let's look at the first class where I believe most of you are familiar with from your introduction solid state 1, which is a paramagnet. Okay, so these magnetic properties exist for free atoms with an odd number of electrons or partially filled inner shell levels, and that is precisely what we mentioned previously, that by following the Hong's rules, some electrons may not find their partners, so they are unpairs, and they are also they're partially filled inner shells. And the second important class of the paramagnets is actually ordinary metals, which we'll see this at low temperature limits. So those are called polyparamagnets, which we already mentioned briefly previously, right? So in such systems, we have a net magnetic moment mu defined by this minus g, where g is a g factor times Bohr magnetone mu b times the total angular momentum vector j. J is given by L plus S, and the total angular momentum j carries the eigenvalue, magnitude j times j plus 1, and angular momentum L square has this eigenvalue L times L plus 1, and S square has this S plus S1 as the eigenvalue. So everybody knows that. And the G factor is simply just 1 plus this 1 over 2 times J plus 1 and times this bracket stuff. It may be a good homework exercise to actually review this, how you get this G factor from this partially filled materials in quantum mechanics, also in introduction solid state. So this is homework. Derive this G factor. But for the simplest example of this magnetic moment is actually the spin 1/2 system. You know that from your quantum physics undergraduate that you have a single electron could take the plus 1/2 or minus 1/2 h bar of angular momentum, and in the fields, these two states are splitted by amount of 2 times mu b, right? And in the presence of the field, this will generate the Zeeman energy, which is minus spin angular moment mu dotted this Zeeman field b, which is given by mj times g times this mu b times the field strength b, where this mj takes just plus minus 1/2. And g is what? G is actually 2, right? So because this is there's no orbital angular momentum, and j is the same as s, so you get cancellations of the numerator and denominator. You get 1 plus 1, which is 2. So in the simple single electron spin in the presence of field, you get precisely this energy, Zeeman energy, which is plus minus mu b times b. And therefore, at finite temperatures, this spin up state and spin down state, the number associated with the spin up and spin down states shows different probabilities based on this Boltzmann distribution. Remember that, okay, in your statistical mechanics, that for the spin up states, which is what higher states or lower states. Let me see. So mu is minus. Yeah. Okay. So this is plus. Spin up state. This is spin down state. Okay. So for the spin up state, the number associated with that state is given by the Boltzmann weight, which is, in the denominator, you get this, all sum over these two Boltzmann weight, which is your partition function, and the numerator, this is the, exponential of this, your energy divided by the KBT with a minus sign. But there's a, and for spin down state, you get this, but with a minus sign there. So now you can see that there's a difference between this number of spin up and spin down electrons at finite temperatures because of precisely this numerator here in the exponential form with different exponents. This is plus, but this is minus. So now we could simply just subtract one from another, and we get the net magnetization n, which is n times this magnitude of the magnetic moment mu times hyperbolic tangent of x, where x is defined by this mu times b divided by kBt, where mu is given by minus mj g times mu b. Okay, so in the high temperature region, you could simply just take advantage of this approximation that this mu b over kBt is really, really small, so hyperbolic tangent is approximately given by linear in x. And that is precisely what you see from the textbook, that the magnetic susceptibility, which is the ratio between the magnetization to the applied magnetic field, m over b, which is 1 over t Curie law, with a proper prefactor c. And in high temperatures of these materials with partially filled inner shells show this Curie law, 1 over t behavior of the spin susceptibility as a function of the temperature in the high temperature region. Okay, so but you could imagine that if you have many electron spins involving here, or orbital or angular momentum involved here, so you get this complicated G factor, but still apart from this prefactor C, you always get this Curie law. The benchmark or the hallmark of this paramagnet, namely in high temperature, you get a Curie susceptibility. So let's look at another different behavior of the paramagnet called Pauli paramagnet, which occurs for all the metals in the low temperature limit, whereas temperature is much lower than the Fermi temperature. So we already explained this diagram in the early lectures. Remember that when we discussed this thermodynamic observables of metals, and in particular the specific heat measurement. But now let's look at magnetization. Okay, so again, for metals, you get density of states versus the energy, as shows such a kind of a parabolic shape. And if you apply the magnetic field in the low temperature limit, you know that this will shift the density of states profile for spin up electrons respect to the spin down electrons. So spin down electrons bands get shifted upwards, while the spin up bands get shifted down. Okay, but the chemical potential is still the same. It doesn't change their chemical potential. So in other words, in such a case, the number of spin up electrons and spin down electrons are not the same because of this shifting of the density states, and the shift is actually 2 times mu times b, where mu is the magnetic moment. So we could estimate, again, the number of spin up electrons and number of spin down electrons from your solid state 1. Namely, you could consider this as zero temperature limit. So you simply just integrate over the density states of the shifted bands. The spin up electron number is given by the integral from minus mu b energy to all the way to this epsilon f Fermi energy, and you integrate over the density states of the shifted band, which is approximately given by the half of the density states plus some shifts, which is 1/2 times mu times b times density states. And likewise, you could estimate this number of spin down electrons in the same way, but now you should shift your band in the opposite direction, right? So this is density states, a function of epsilon minus mu b, whereas in the spin up case, this is density states, function of epsilon plus mu b. So then you could again estimate this from this Taylor expansion of the density states near the Fermi energy. So this is given by, again, this half of this density states integrated from 0 to this Fermi energy minus the same amount. So you can simply just take the difference between these two numbers. You get the net magnetic moment, magnetization, which is mu squared times density states times your field strength. And you take the ratio between m and b, you get a constant, which is proportional density states. And that constant density states is the correct description of a Pauli spin susceptibility. So this is called the Pauli spin susceptibility, meaning in low temperature, zero temperature limit for all the metals, which shows such a Fermi surface and this density state profile will lead to the constant spin susceptibility, which we call this Pauli spin susceptibility. Okay, so this is the introduction to the paramagnet. So let's take a short break. We'll come back and we'll introduce another class of magnetic material, which we call this ferromagnetic material. Okay, so let's continue. The second class of magnetic material is called ferromagnets, and we know very well in nature we have such a ferromagnet, or as we know that the magnets, okay, are made of iron, okay, and another well-known examples of ferromagnets are called cobalt or nickel, and so on. Okay, so the common features of these materials that they have spontaneous magnetizations at low temperatures, and to explain why they behave such a peculiar properties that they have a spontaneous magnetization at low temperatures, this could be understood in terms of the spins and spin interactions. So since those materials shows partially filled inner shell levels, so there should be a net magnetic moment, spin moment, that's for sure. But as we pointed out just earlier, that many materials with a partially filled inner shell don't have such a spontaneous magnetization at low temperatures because their spins are sort of randomly distributed, and the spins don't talk to each other. So there's no spin-spin interactions in those non-magnetic materials, even though they are partially filled, and at high temperatures they show such a Curie behavior. But this ferromagnetic materials are different because the spins of these unpaired electrons, they do talk to each other. They they simply know the existence of their neighbors. Okay, in other words, they have a very strong spin-spin interactions, and the reason why they have such a spin-spin interactions are due to those Hahn rules couplings, and also this kind of exchange interactions between electron spins. But you could roughly use a model to describe such spin-spin interactions in the ferromagnetic materials. Namely, this is the Si dot Sj type of spin-spin interactions with a prefactor Jf called the ferromagnetic exchange coupling, which is minus, which is negative, okay, minus magnitude of J. And you know very well from quantum mechanics that in order to reach the ground state, if you have a minus sign in front of a Hamiltonian, which is Si dot Sj, and to minimize the free energy, the Si must be parallel to Sj, right? Okay, where I and J refer to different sides of the magnetic material. So each side, you can imagine, can attach a spin moment there with either spin up or spin down, or even greater than spin 1/2 spin moment. But those spin moments are coupled together in the ferromagnetic way, so that those spins moments are perfectly aligned to each other, a low temperature limit, and because they have such spin-spin interactions. But effectively, you can imagine that such the spin coupling could be viewed in terms of a so-called effective magnetic field or exchange field due to the spin-spin interactions between for example, neighboring spins. For example, if I consider a spin moment on side I, but you know that Si couples to its neighbors, say I plus 1 or I minus 1. Right? But if you consider this Si dot Sj, where J refers to I minus 1 or I plus 1, you could immediately recognize the form of this kind of a spin-spin coupling looks very much similar to the Zeeman form, right? So the Zeeman form is what? S dotted B, right? Or mu dot B. Okay, so you could imagine that the spin moment on neighboring sides could actually produce the effective field to couple to the spin on side I. And such a effective field generated by the spin moments of the neighboring sides is called the exchange field. It looks like there is a magnetic field, effective magnetic field, because this coupling between the neighboring spins look more or less like the Zeeman term. And the Zeeman term is a coupling between the magnetic field to the spin moment, magnetic moment. So this B, plays, the spin on the neighboring sides plays the same role as the magnetic field in the Zeeman form. So we call this B field exchange field, which is the effective field, applied to some specific site with a spin moment that, contributes to from the neighboring spins. And we call this Curie-Weiss mean field, okay, for the reason that we could use some kind of a self-consistent mean field, a method to actually derive such a spontaneous magnetization from this Weiss mean field. But in any case, this effective magnetic field or exchange field is actually internal magnetic field. Okay, you can imagine that spin moments plays the same role as a magnetic field coupled to the neighboring spins, and this, is kind of an internal magnetic field which is proportional to magnetization. So this is kind of a self-consistent way of thinking. This magnetic field itself is made of spin, and so it leads to the kind of magnetization all the sites. And so we can imagine that this exchange field is linearly proportional to magnetization with some proper prefactor lambda. So that's our kind of a toy model to understand this ferromagnetic behaviors. So again, at high temperatures, we can imagine that such a magnetization is actually shows the Curie law because they have partially filled spin there. Okay, but the difference here from the paramagnetic material is that we have an internal field, effective exchange field, in addition to the applied field. So the total magnetization, is a function of this field, but this in terms of the total field, but the exchange field is actually linear proportional to the magnetization. So you see these two are coupled together. And the prefactor, we call this paramagnetic spin susceptibility, which is a Curie-Weiss behavior. That's what we expect at high temperatures. So you see, this is the existence of the exchange field is the difference between the paramagnet and a ferromagnet. In the ferromagnet, we do have such exchange field, which is linked to the magnetization itself, so that these two are really coupled. However, in experiments, what we really measured is the ratio between the magnetization to the applied field. So you only take the ratio between M and B applied, and you don't include this exchange field in the definition of your susceptibility measurement. Okay? But you could actually solve these two equations simultaneously and get the ratio between M and B applied and take advantage of the fact that these systems shows the Curie law at high temperature. So when you plug in everything, you get this Curie law constant C divided by T minus C times lambda, where C is the prefactor in front of the 1 over T Curie law, and lambda is the prefactor which couples the magnetization and exchange field. And so it gets very much similar to the Curie law for the paramagnet, except now I get a transition temperature Tc, which is defined as C times lambda in a denominator here. Okay, so that when T is above Tc, you get more or less this Curie law, right? But it hits infinity or it diverges when T becomes Tc. And that is precisely where the spins are ordered. Okay? So all the spins are ordered when temperature is below a critical temperature called ordering temperature Tc, but above Tc. So the spins or magnetic moment actually disordered, or they're randomly distributed, so that they follow the paramagnetic behavior. But as long as you lower temperature to below Tc, all the spins are ordered. And this is the phenomena for ferromagnets. That if you take a measurement of the spin susceptibility of a ferromagnet, you come from the high temperature, and you see this perfect Curie law, 1 over T behaviors, until this temperature reaches this ordering temperature Tc, that susceptibility diverges. And below Tc, since all the spins are locked into this parallel configuration, so you get almost vanish of this susceptibility because there is no response when these spins are ordered. Okay, so that's the physics of the ferromagnet. So let's look at the third type of the magnetic material called the antiferromagnet, which is very much related to the ferromagnets, except now for those materials such as manganese oxide or copper oxide, we have two sublattices, and each sublattice looks like a ferromagnet. For example, you have a sublattice A, where all the spins point up, but you have another sublattice B, which is just next to sublattice A sites where all the spins point down. So if you look just at each of the sublattice A or B, they look precisely the same as ferromagnets. But then there's two ferromagnets with opposite spin orientations, they actually get interlocked together. Okay, you get this kind of a AB, up, down, up, down, up, down, up, down. And this is what we call antiferromagnet. And there are many examples of antiferromagnet in solid states, and this is just some of them. So many interesting examples of antiferromagnets are from the strongly correlated electron systems. For example, the cuprates, high TC superconductors, and so on. And of course, just like the ferromagnetic case, that the reason why they have such a strange orientation that they have up, down, is because they have exchange coupling, J antiferromagnet, which is positive, which couple to the neighboring spins, so that to minimize the free energy or Hamiltonian, the orientation of the spins on neighboring sides should be along the opposite directions. So if spin on side I, where I refers to sublattice A and J refers to sublattice B sides, then either all the spin on the side A sublattice point up or point down, but if A points up, B should also should automatically points down, and vice versa. So there is a long range order between the spins on sublattice A and spins on sublattice B. So it doesn't matter how far away the two spins are, they always have this perfect up, down, that type of alignment, right? So, and this relation could be very long range, okay? So because they are tightly linked together. And we know that this magnetization on side A is actually opposite to the magnetization on side B. And we also know that there's exchange field, just like in the ferromagnet, but here the exchange field on side A sublattice, come from the magnetization on side B. And so the exchange field on the side B is actually contributed from the magnetization on side A. But you know this MA is actually minus MB. So that's the non-trivial part of the antiferromagnet. Okay, so let's stop here. We will finish this calculation on the thermodynamics, especially the susceptibility for antiferromagnet next time, based on this kind of a toy model and this understanding of this opposite orientation of the spin moments on sublattice A versus sublattice B. Okay, so I see you next time.